All right, let's dive into electrostatics. It's a huge part of physics, and yeah, it's a topic that can really make or break your score in competitive exams like the JEE. It's all about charges that are standing still, but trust me, the problems they create are anything but static. So, how do we get a handle on it all? Well, we're going to build a toolkit together to crack the electrostatics code. First things first, take a look at this. We've got a cube sitting in an electric field that isn't even uniform. And the question is simple. How much charge is hiding inside? Now, your first instinct might be that this is going to require some seriously heavy-duty math, right? A bunch of integrals maybe, but what if I told you there's a much smarter way to get the answer? And that's exactly our mission today. We're not just going to grind through problems. We're going to build a conceptual toolkit, piece by piece. By the end of this, you'll have 3 fundamental tools that will let you look at a complex electrostatics question and just see the simple path forward. Okay, so before we can start solving these kinds of problems, we need to learn the language. And the language of electrostatics all begins with one single, all-important idea: the electric charge itself. So, what is charge, really? The best way to think about it is it's like mass. It's not something that matter has, it's just part of what matter is. It's this fundamental property that tells a particle how to behave when it runs into electric and magnetic fields. It's basically the source code for everything we're about to explore. And this charge, it plays by a very strict set of rules. It's additive, you just add it up. It's conserved, you can't create or destroy it, only move it around. And, this one's a big one, it's quantized. It only comes in these tiny, indivisible little packets, the charge of a single electron. These are the fundamental laws of this invisible world. And here we go, our very first tool for the toolbox, Coulomb's law. This is your go-to formula for the most direct question in all of electrostatics. How hard are 2 little charges pushing or pulling on each other? It's simple, it's powerful, and it works for any 2-point charges anywhere in the universe. But what happens when you don't just have 2 charges? What if you have a whole collection of them, or a charged object? Using Coulomb's law for every single interaction would be a total nightmare. The calculations would get out of control fast. We need a better way to see the big picture. And that brings us to our second tool, the electric field. Instead of calculating a million different forces, we just draw a map. Seriously, think of it like a weather map. But instead of showing wind, it shows the strength and direction of the electric force at every single point in space. It's an incredibly clever and useful idea. So how do we draw this map? With electric field lines. They show you the exact path a tiny positive charge would take if you dropped it into the field. So naturally, they flow away from positive charges and towards negative ones. Where the lines are bunched up, the field is strong. And they have some non-negotiable rules. They can never cross because the force at any one spot can only point in one direction. Make sense, right? Okay, so we can find the force between 2 charges, and we can map out the force in a whole region. But what about our cube problem from the beginning? That still looks pretty tough. Calculating the field everywhere and adding it all up sounds awful. We need a master key. We need a brilliant shortcut. And here it is, Gauss's law. And yeah, I know, that equation looks intimidating. You see that integral symbol and all the vectors, and you might want to run. But hang on, let's look past the symbols for a second, because the idea hiding inside this equation is actually beautiful and surprisingly simple. So here's the secret. All that scary math really just says this. If you imagine some kind of closed surface, like an imaginary bubble, the total amount of electric field flowing out of that bubble depends only on the total amount of charge you've trapped inside it. That's it. Any charges outside the bubble, for the net flow, they don't matter at all. It's a mind-blowing simplification. And this, right here, is the heart of thinking like a physicist. The real goal isn't just to get an answer, it's to find the simple, elegant path through what looks like a complicated mess. And for any problem that has some kind of symmetry, like spheres, or cylinders, or, cubes, Gauss's law is that path. It's the definition of working smarter, not harder. Okay, our toolkit is officially built. We've got Coulomb's law for point-to-point forces, electric fields for mapping out the terrain, and Gauss's law as our incredible shortcut. Time to get our hands dirty. Let's head to the workshop and see how these tools actually solve the problem. Here is a classic exam question. You have a charge Q sitting perfectly in the center of a cube. The question is, what's the electric flux through just one of its 6 faces? Now, if you try to do this the hard way, calculating the field from Q at every single point on that face, oh man, it would be a nightmare. But with our new toolkit, this becomes almost trivial. Let's walk through it. Step 1. Use the right tool. We see a cube, we see symmetry, we grab Gauss's law. We imagine the cube itself is our closed surface. The law tells us the total flux coming out of the whole cube is simply the charge inside, Q, divided by a constant. Done. That's the total. Step 2. Use your head. The charge is dead center. That means the situation is perfectly identical for all 6 faces. So that total flux has to be shared equally among them. Which means the answer for just one face is simply the total flux, divided by 6, Q over 6 epsilon naught. And that's it. No integrals, no complicated vectors, just 2 steps of pure, simple logic. That is the power of choosing the right tool. So let's circle all the way back to that challenge from the beginning, that intimidating cube in the non-uniform field. Let's take another look, because now you have the exact tool you need to see right through the complexity. You're ready. Remember, the electric field only had an X component. That means it runs parallel to 4 of the cube's faces, so 0 field lines poke through them, no flux. On the face where X equals 0, the field itself was 0, so again, no flux. The only face that contributes to the net flux is the one on the far right. Once we calculate that one value, Gauss's law tells us the charge inside is just that net flux times our constant. Problem solved. And there we have it. We've built a powerful set of conceptual tools. We looked at problems that seemed really tough on the surface, and we found a clear strategy to break them down. So let's lay out our complete toolkit one last time. This is the strategy you should take away. Got 2-point charges and you need the force? That's Coulomb's law. Need to understand the influence over a whole area? Think in terms of electric fields. But the moment you see a problem with symmetry, your brain should immediately yell Gauss's law, because that's your power tool. Mastery here isn't about memorizing formulas. It's about recognizing which tool makes a hard problem easy. And remember, this isn't just about acing an exam. These are the fundamental rules that hold our atoms together. They're what power the very computer or phone you're watching this on right now. The universe is speaking this language of charge and fields. Now that you're learning to understand it, what will you build with it?